In this video, we will consider several definitions, but before giving the statements, let me summarize what we have seen so far. We have defined an algebraic function field as a finite extension over the rational function field k of x, and we define a valuation ring, and we consider some examples in the simplest case rational function field. And by proposition 8 and theorem, the last theorem, theorem 10, we have seen that the local ring is this, valuation ring is also a local ring. So that means it has unique maximal ideal P, and this is also principal ideal domain. And a principal ideal domain with unique maximal ideal is called a discrete valuation ring. Principal ideal domain which has unique maximal ideal is called discrete valuation ring. So that means thanks to the last theorem and proposition 8, we can also see that valuation ring is also discrete valuation ring. And its maximal ideal is generated by T, and thanks to this generator, we can represent every function in an algebraic function field F in terms of the powers of the generator of P and in terms of the units of evaluation ring O. And as we have seen, they play an important role in the structure of the function field, in the structure of the elements from a function field. I think they deserve spatial names. And this maximal ideal is called a place of a function field, f over k. A place P is the maximal ideal of some valuation ring of F. And its generator as a principal ideal will be called a prime element for P. And here note that this generator is not supposed to be unique. Prime element for P. And if you are familiar with algebraic geometry, you may also come across other keywords like local parameter or uniformizing variable of P. And the set of the places of a function field will be denoted by P sub F. And later we will see that this is indeed non-empty step, so there exists always a place in a function field. And moreover, we will also see that there are infinitely many places. Infinitely many places in the set PF. And we will also see that this set is also is one-to-one, is in one-to-one correspondence within the valuations in a function field. And actually, we know how to define, and for a given valuation, we know how to define its maximal ideal. And conversely, for a given P, by proposition 8, part 2, by using this characterization, we can also identify O for given P. It means it contains the elements X in not in P. X not in P if and only if X inverse in O, X inverse not in P, X in O. So let me correct my mistake. X inverse not in P. And another ingredient which will allow us to identify or to work with valuation ranks and the places will be the discrete valuation map. So first, let me give the definition and then explain what kind of correspondences do we have. We will define a map on a function field f, which will be denoted by V, and that satisfies 5 properties, which are given as follows. And first property tells us this valuation is infinite if and only if X is the zero element in F, and the valuation of multiplication of two elements is equal to the addition of the valuation of each element, and the valuation of X plus Y is bounded below the minimum of V of X and V of Y. And fourth property tells us there exists Z in F such that its valuation is 1. And here, let me mention that thanks to this property, we can say that V is indeed surjective because for any integer m, if you consider the function z to the m in f, its valuation will be m times v to the z from part 2, the second property, and since valuation of z is 1 because we choose z with this property, we see that for every m we can find a function in f. So this is surjective. And the last property tells us that the valuation of any non-zero constant is 0. So for this definition, first let me give an example. In this example, let me consider a rational function field with coefficients from the binary field f2. And we will define the valuation of a polynomial f as minus its degree, its polynomial degree. And we extend this definition for the fractions f over g as degree g minus degree f. Here f and g are polynomial and this is an element in a rational function field. And to see that the valuation of 0 is infinity, actually Vx is 0 if and only if, V of x is infinity if and only if x is 0. Let me check briefly by applying the definition of valuation for the 0 polynomial, and conventionally we define it as infinity. Otherwise, it cannot be infinite. And for the second, to check the second property, let me consider fractions f over g and a over b. And just applying the definitions for the rational functions, we obtain degree of g times b minus degree of f times a. And the degree of the multiplication of polynomials is equal to the degree of their summations. And by rearranging this statement, we can see that this is equal to valuation of a over g plus valuation of a over b. To prove the third statement, I only consider the simplest case. So that means I'm going to prove it only for polynomials f and g.